perovskite oxygen permeable membrane reactor for hydrogen and syngas co-production.
Yeah, thank you. Thank you for the kind introduction, and thank you everyone for coming to my talk. So I know that it's a very long title, so briefly I will talk about the design and the cost analysis of this type of membrane, and we'll talk about an oxygen permeable membrane reactor, and the goal of this reactor is for hydrogen and syngas co-production. So the outline for today, I will give you a brief introduction of hydrogen as well as syngas productions, and then I will talk about the design of this membrane reactor for this co-production purpose, and then I will talk about the economic analysis of the membrane materials compared to of the very conventional heavily started membrane materials. So first of all, let's talk about syngas. So syngas is a mixture of CO and hydrogen, and syngas production actually depends a lot on the resources as well as the local markets. And you can see that this is a prediction of the global syngas production, and you can see that the most growth recently is due to China, which is usually use coal gasification, and the demand for syngas is mainly for methanol production, olefins, as well as fertilizers, which is ammonia and urea. And if you look at the syngas production, actually in most of the places that use natural gas as a feedstock, is heavily depending on the natural gas price. And you can see that nowadays it's around $2 per 1,000 cubic feet of syngas, which is very close to a hydrogen price. On the other hand, if you look at hydrogen, and hydrogen, as we know, is an energy carrier, and it's also a commodity. And the reason is you can look at this is the hydrogen production of United States. You can see that the captive here is the blue bar is the on-site hydrogen production, and the merchant, which is the red bar, is the off-site hydrogen production. And you can see that the on-site hydrogen production, it keeps very stable, and there's a lot of increase in off-site, which is the centralized hydrogen production plant. That's you produce hydrogen, and then you use a hydrogen pipeline to transport this hydrogen to the place that you need the hydrogen. But if you look at the hydrogen production these days, you can see that almost all of the hydrogen is from hydrocarbon. Only 4% is from water. So that means if we use natural gas, oil, coal combustion, coal gasification to produce this hydrogen, and this type of hydrogen is no longer clean because it emits a lot of CO2. So just briefly talk about the CO2 emission of this hydrogen production using different sources. And you can see that if we assume the gasification is 80% and natural gas reforming is 90%, and then you can see efficiency, and then you can see that coal gasification actually emits a lot of CO2 compared with natural gas power plants. So that's why in our lab we developed a technology that we can co-produce hydrogen and methane, syngas, and without carbon emission. So this is the schematic of the plants. So for example, we have water on one side, it will split into hydrogen and oxygen. And because in oxygen permeable membrane we're talking here, so the oxygen will permeate through the other side of the membrane, react with methane, partially oxidize the methane, to produce a syngas which has the hydrogen to CO ratio is 2/1, which is optimum for methanol production. And so what type of membrane we're talking? So this is the perovskite membrane that we are talking that can conduct oxygen. So here is a schematic of the process. So on one side, we have water diffused from the gas onto the membrane surface, react with the oxygen vacancies so that the oxygen from the water would diffuse into the lattice while we produce hydrogen on that side of the membrane. And then the oxygen from the lattice would diffuse to the other side because of chemical potential gradients. And on the other side, we have this lattice oxygen. It's reacting with this methane so that we can produce a mixture of CO and hydrogen. And compare this with the conventional technology, there are a lot of advantages, which I summarize here. So here again shows our process that we have water and is producing hydrogen. So here I use a pure hydrogen production as as an example. So we produce hydrogen from the water, and we consume all the methane as an energy source, basically. And the conventional hydrogen production uses a steam reformer and a gas shift reactor, and also a pressure swing absorption to purify the hydrogen. So you know that there are lots of different reactors, and it's a very complex system. So that's why what we are talking here, there are several advantages for our technology. So first of all is we can integrate renewable heat and electricity, which I will talk about later in our presentation. And then the second advantage is that it institutes separation of hydrogen and other products. So that means we can increase the hydrogen recovery as well as the CO2 capture ratio. And also, you know that we only have one reactor and it's isothermal operation. That means that the operation as well as the maintenance cost of our process is much lower than the conventional methane reforming. We did analysis to compare these two different technologies. So we use a system scale analysis to compare the steam methane reforming, which is the conventional technology, with our new technology to use a methane membrane reactor. So you can see that actually the efficiency is quite close to the conventional technology. However, the conventional technology utilizes only methane as a fuel or as a source for the hydrogen production. However, in our technology, we can use some of the methane to hydrogen production, and then we also integrate some type of renewable or low carbon heats. So that, for example, this is an example that if we have a solar heat at this temperature, at around 300 degrees C, which is easily obtained from a solar thermal power plant. And then 30% of this external heat actually can be from the solar. So that means that we can incorporate this low temperature solar into our system. And also because, we have a cost reduction compared to the solid oxide electrolysis cell, which is shown here. That we also did a cost analysis. So this is the high temperature solid oxide fuel cell, a solid oxide electrolysis cell, and this is the methane assisted processes. You can see that there is a big decrease of the cost reduction produced a high purity of hydrogen. And because of this, our technology has actually entered the final round of the Hydrogen Refuel Accelerator program and attract a lot of attention from, for example, Toyota, Shell, to develop this type of technology into a distributed hydrogen production plants. So based on this, we know that this is efficient as well as a low emission, and also cost is reasonable. However, you can still see that the capital cost of our plant is still high. So that's why in order to further decrease the hydrogen production, we have to further decrease the capital cost. So that's why in and the second part, I will talk about how we can analyze this membrane reactor and how we can try to decrease the cost of the fabricating this type of membrane reactor. So this is one of the examples that we used in the lab. We use a monolith membrane reactor, and you can see that monolith is like this, has a lot of channels. And the membrane itself is made from the perovskite material that I mentioned earlier. So the feed side, the water side, and also the methane side actually is alternating. So we have one channel of methane and the other channel is water, so that the oxygen can permeate through this membrane and make utilize of all the surface area of this membrane. And if you look at a 2D schematic, you can see that on one side we have water and oxygen diffused, and on the other side we have methane. So in order to model this process, I used a 1D reactor model developed from MATLAB, and also we used the kinetics from based on the water feed and methane swim processes that is reported in the literature as well as derived in our lab. So the advantage of utilizing this kinetics model is because it enables the reactor design, because we consider the kinetics of the reactions and we are no longer limited by the thermodynamic equilibrium model that is usually used in the literature. And the base size of the reactor is very similar to the solid oxide electrolysis cell as well as the solar reformer. So here shows the kinetics model that we used in our lab. So this is the kinetics model that, as I mentioned, so this is the flux, and we consider the potential of oxygen flux over some of the resistance of this oxygen permeation. So as I mentioned, there were several steps of this reaction. There are several steps in this process. So for each step, I ascribe a resistance for it. So this model actually fits the data very well. So I used a very well started, so the lanthanum calcium iron oxide membrane is what we started in our lab. And we also used the barium cobalt iron zirconium oxide membrane, which is from the literature. So it fits very well with using this type of kinetics model. So based on these models, now we can determine how long the reactor is and what is the size of the reactor. So that's why, so the goal of this study is to determine the length of the reactor. So the reason that we want to determine the length is because, as you know, that when we have water is converting and then the concentration of water is very low at the end, at the outlet of the reactor. So at the outlet of the reactor, the membrane surface is actually not very effective. So that's why we want to have a determination or criteria of how long this reactor will be so that we can achieve 90% of the methane conversion on that side of the membrane. So we did some analysis of different parameters. For example, we tested some different flow rates for these two types of membranes. And then we know that the goal is to identify that the 90% methane conversion rate. So here shows the two of the parameters that we two flow rates that we chose. So for an LCF membrane, we chose that is 4.2 SCCM flow rates, and then this is the length. And then for another reactor, we chose a higher flow rate because it has higher flux. So the results shows here that so we use the same membrane thickness, and then we use the same membrane channel height, and we have we have very similar length, but the flow rate is different for the two reactors. So that's why it's when we so we also did another analysis, a sensitivity analysis, to determine different parameters and how they can impact the design of the membrane, which is the length of the membrane. So we compared the sensitivities of the geometric of this membrane reactor, also the kinetics of the membrane reactor, as well as the operation conditions of this membrane reactor. So the result shows here that you can see that the length of the reactor is very sensitive to the height of this monolith channel. So that means that's because of the mass diffusion barrier of this inside this channel due to the very low flow rates in our reactor. And then another thing to notice is that the kinetics is also very important, as well as the operating or the concentration of these gases is also very important. However, the thickness, also the diffusion of the vacancies is not very sensitive because of the high oxygen permeation of these membranes in our studies. So based on this, we analyze, so for example, for small hydrogen power plant, hydrogen production plants, that we want to use 100 kilomole of hydrogen per hour production rate, how much surface area that we want to have for different type of membrane materials. And you can see that for LCF membrane, which is not as good as the BCF membrane, it has much higher surface area which is needed. And then we also compare the cost of this membrane based on the raw material cost. So here we have from Alibaba website, we derive the cost of different mineral sorts that we get from these vendors. And we compare the cost, and you can notice actually the cobalt is much expensive than other materials. So the result shows that the LCF membrane, even though the cost of the material is less than half of the BCF membrane, however, because you use a lot of more materials, so that's why the total cost of this is higher compared to the BCF membrane. But you can also see that there's an arrow bar here. That means that the the cost of the materials is actually fluctuating during the time. So that's why there might be a time that these two materials, these two membranes might cost the same. So that's why we did a sensitive analysis again based on to see these materials cost dependence on the cost of the minerals. So the results are showed here. So again, the base case for LCF is very expensive, as I mentioned. And then the BCF membrane is much cheaper because the less surface area we utilize and also because of the higher performance. However, you can see that if the cobalt price doubles, and then this membrane is actually will be very close to the LCF membrane cost. And also, if the lanthanum cost is half the price of now, and you can also see that the cost of these two membranes might overlap at some point of the prediction. So that's why when we analyze and when we use different type of materials, we would like to consider the cost. And also, for example, for cobalt price, it's expected to keep increasing. However, for lanthanum, the price will keep low and maybe drop beyond this year, as the analyst said. So to conclude, we did an analysis of this oxygen permeable membrane for hydrogen and syngas co-production, and we analyzed this type of reactor for small-scale hydrogen production plants, and we realized that because LCF is not as good as the BCF for the performance, actually has much higher, needs much higher surface area. However, the BCF membrane is more expensive due to the cost of cobalt, but the overall cost of the LCF membrane reactor can be more expensive at this moment compared with the BCF membrane. However, because the cost of cobalt is very volatile and is unexpected, so that's why a lot of the research now is looking into whether we can use some of the membrane without cobalt. However, we also can match the performance of this BCF membrane. So I would love to thank your attention and also thank my lab mates and also the sponsor, Excellent Corporation, for sponsoring this project. And thank you so much. I would love to take any questions that you have. Yes.
An interesting talk. I wonder the hydrogen purity in your terminal product.
Yeah. So what we so as you notice that the reactor is so the hydrogen is from the water side. So actually we can condense the water and get easily get high purity of hydrogen. Let me see. Yeah. So and also this
So there are
yeah.
two products.
Yeah.
One is from water sleep.
Yeah.
Another is massive conversion.
Yes. So that's why we look at, so for high purity of hydrogen, we look at the water side, which can derive very high purity of hydrogen. And for the methane side, this syngas is for methanol production using a catalytic reactor. So they have different applications. Yes. Yes. Yeah.
Yes, thanks for the presentation. I have a question regarding the reactor. And you say that you use the solar heat, but at the same time, I don't see how you maintain the temperature on the reactor, or how you actually do that coupling between the solar heat, or maybe you introduce the reactor at some temperature, but then you cannot maintain the temperature, which of course is very important for the membrane reactor.
Yes, that's right. So I didn't show that actually the operating temperature is, the reactor performance is very sensitive to the operating temperature. So that's why in our analysis, we assume it's isothermal. But there is a lot of engineering way to integrate this reactor into solar. For example, shining the concentrated solar power directly to this membrane reactor, or by heating up the membrane so that by heating up the inlet gases. So in that case, it might not be isothermal. but it will be another.
But the thing is, yeah, I know that you didn't have time for the technical details, but if you integrate directly, you have the problem of the transient during night and days, and I think it's not necessary for that thermal level. And if you put in the inlet, since you are producing syngas, it's quite endothermic, so you just
Will decrease the temperature. Yeah.
And, it's an important thing. So have you thought how to do it in practice or?
Not at this moment. Yeah, but there are some opportunities.
Because maybe with production of CO2 and hydrogen and CO2, so complete combustion of the CH4 instead of syngas, you have more or less the same temperature, but then it's not so interesting because you are not producing syngas, you are producing CO2.
Yeah. So the thing is, so in our process, we can also burn some of the methane to produce the heat if we don't have solar. And in that case, and since because we have hydrogen and methane is separated, so that there might be an optimized operating mode for that purpose. Yeah.
I have an idea.
Okay, good. We have to discuss that.
Or later.
Okay. Yeah, thank you so much.